Okay, today we're going to be talking about symmetry. And essentially, when you have a relation, there are three different types of symmetries that we want to be aware of. And the first is when a graph is symmetric to the x-axis. And all that simply means is that I could take the graph and I could flip it over the x-axis and it looks exactly the same. And then you have symmetric to the y-axis, which you take the looks pretty much the same on the right of the y-axis as it does the left. You can take the part of the function on the right and literally flip it around over the y-axis and it looks exactly the same. And then symmetric to the origin. Essentially what you have is you have something that you could flip it over the origin and it would look exactly the same. So opposite quadrants are the same. And so the test that we have here is that no matter what you plug in for y, if you plug in either y or the opposite of y, you get the same result, same x, right? So you go over some x and up y, over some x and down y. So regardless of whether you plug in a positive y value or a negative y value, you still get the same result for x. And here, same idea. If you plug in x or f of x, negative x, you still get the same y value right there. Now here, it's a little different. If you have this point xy, then if you plug in the opposite of x, you will get the opposite of y. So how does that look? Well, f of negative x is going to equal negative f of x. Now let's make sure that's understandable. F of negative x means to plug in the opposite of x. Well, f of x is another way of saying y. So what happens when you plug in the opposite of x for an odd function or symmetrical to the origin? You get the opposite y value. So let's see how this works on a few sample problems. Okay, here in this example, we see that this first graph appears to have symmetry about the y-axis, because it looks the same on the right as it does on the left. But we're going to test this out. We're going to test this out by picking a random number. And so as you remember that the test for this is going to be f of negative x must equal f of x. So I'm going to pick a random number and I'm going to pick 2. So the question is, does f of 2 or f of negative 2, do they equal each other? Well, let's see. F of 2 is going to be negative, and then parentheses 2 squared plus 6. 2 squared is 4. Multiply that by a negative. That's negative 4 plus 6. That is going to be 2. Well, f of negative 2 is going to be negative, parentheses. Be careful to leave the negative outside the parentheses and put the number inside. Well, when you square negative 2, that's also going to be positive 4 times negative, which is a negative 4, plus 6, which is 2. Because f of 2 and f of negative 2 are the same, then we can conclude that this has symmetry about the y-axis. Okay, we're going to do the same thing over here. This appears to have symmetry about the y-axis and about the x-axis. So let's see if we can do the same deal. We are going to plug in, let's just say 2. And let's see what we get. 2 squared is 4 plus y squared. Well, actually, you know what? Let's do it this way. We are going to plug in 2 for x. That's going to be 2 squared plus y squared equals 25. And that's going to be 4, and so y squared equals 21. So y equals the square root of 21 plus or minus. And let's see what happens if we plug in a negative 2. Well, negative 2 squared plus y squared equals 25. Negative 2 squared is 4. So we're going to get y squared equals 21 again, and then you take the square root, y equals plus or minus root 21. And you can see that the same exact thing is going to happen. I'm not going to take the time to go through it, but the same exact thing is going to happen if we plug in a positive y value and a negative y value. We're going to get the same x's whether you plug in a positive or a negative. So when that happens, you can say that this is symmetric about the y-axis and it is symmetric about the x-axis. This one is symmetric only about the y-axis. Okay, so now we see that we're going to look at functions here, and the reason why that we don't really pay much attention to symmetry over the x-axis is because that is not a function. It is not a function because it doesn't pass the vertical line test. So once again, something that looks like this, it does have symmetry once again over the x-axis, but it flunks the vertical line test, which makes it not a function, only a relation. So therefore, we are going to only analyze functions, which means that it can either have what's called even symmetry or odd symmetry. Even symmetry, once again, think of your face as even symmetry. Even symmetry means it looks the same on the right as it does on the left. Odd symmetry is, once again, it's going to be the same in opposite quadrants. So they both start with O, odd and opposite. So this is odd symmetry, this is even symmetry. So let me give you a little hint here. One of the quickest ways to figure out whether a function has even symmetry or odd symmetry or neither is to look at the exponents. All right, notice that the exponents are a 3, that's an odd number, and then there's a hidden number 1 here, that's also an odd number. So that tells you that this function has odd symmetry, but we still have to prove it. And so what we're going to do is we're going to pick a random value for x. And so if you remember the odd symmetry is going to be f of negative x is going to equal negative f of x. Once again, plug the opposite x in, you should get the opposite y value. So it should look like this. But let's prove it. So we're going to plug in, random number. I'm going to say 2. 2's been working for me. So this test says, once again, if you look up here for odd, that if I plug in a negative 2, I should get the opposite of what I get when I plug in a positive 2. Let's see if that's true. Well, negative 2 to the third minus 2 times negative 2. Let's see what that is. Negative 2 to the third is going to be a negative 8. Negative times a negative is a positive 4. So that's going to be a negative 4. Now, let's see if that's equal to the opposite of what I get when I plug in 2. Well, let's see. Negative, and then I'm going to plug in 2 into this function right here and right there. So 2 to the third minus 2 times 2. So 2 to the third is 8 minus 4. Well, that's just going to be 4, but when you multiply by a negative, it's going to be a negative 4. So I want you to notice that that answer and that answer is the same. Therefore, you can conclude that this has odd symmetry. In example B, we have g of x equal to x to the fourth plus 2. Well, once again, I can look at this and tell that it has even symmetry. The reason is because the exponents are even. Well, this is an even number, x to the fourth, and you may not realize this, but there is really an x to the 0 here. Keep in mind that anything to the 0 power is 1. 3 to the 0 is 1, 5 to the 0 is 1, x to the 0 is 1. So you could call 2 as 2 times x to the 0. Well, 0 is an even number, so is 4, so we can conclude that this has even symmetry, but we still have to prove it. So what is the test for even symmetry? F of negative x must equal f of x. What does that mean in English? That just simply means that when I plug in the opposite x value, I get the same as if I plug in the regular x value, which means the function should look the same on the right as it does on the left. Even symmetry. So we're going to pick some random value. I'm going to pick 2 again because I like 2. F of 2 is 2 to the fourth plus 2. Well, that's 16 plus 2, that is 18. And then now we're going to plug in negative 2. Well, parentheses, negative 2 to the fourth plus 2. Negative 2 to the fourth is negative 2 times negative 2 times negative 2 times negative 2. Hey, that's going to be 16 again, plus 2, 18. Hey, these things are the same, f of 2 and f of negative 2. Therefore, we will conclude that this has even symmetry. Okay, last example here is 4 times the square root of x. Now, if you know anything about what this graph looks like, you can tell immediately that this does not have any symmetry. This is just a square root function, looks like this. Well, it has no symmetry at all because there's nothing over here to the left, so it doesn't have symmetry that's even, and there's nothing over here, so that's not odd, but we have to prove it. So therefore, we're going to plug in, well, we're going to do both tests, and let's see what we get. I'm going to plug in a number that I can take the square root of easily. I'll pick 9. So g of 9 is 4 times the square root of 9. Square root of 9 is 3 times 4, which is 12. Uh-oh, there's a problem. When we try to plug in a negative 9, we can't do it because we can't take the square root of a negative number without getting imaginaries. So therefore, because this doesn't exist, it doesn't have even symmetry. And if you pay attention to the odd symmetry test, which is right here, you will also recognize that you'd have to plug in a negative 9 here. And because that does not exist, you can say that this does not have even symmetry or odd symmetry. This has no symmetry. And that's all there is to it, to symmetry of functions.